Hi guys, welcome back to the 12 ISLs of Christmas. Today we're going to be looking at IMO Shortlist 2024 Problem G1. And this shortlist only came out 5 months ago, after the second day of the IMO 2025. And the first problem on the geometry shortlist, which we are looking at today, is a pretty instructive problem in my opinion. So without further ado, let's get started. Let ABCD be a cyclic quadrilateral such that AC is less than BD is less than 80 and angle DBA is less than 90 degrees. Point E lies on the line through D parallel to AB so that E and C lie on opposite sides of line AD, as we see here, E and C, and also AC equals DE. And these are marked by the blue segments. The blue segments have equal length. Similarly, point F is such that AF is parallel to CD, and also the red segments have equal length. And these produce the points E and F. And we want to prove that the perpendicular bisectors of BC and EF, which are marked in orange here, intersect on the circumcircle of ABCD. So how can we get started on this problem? Well, we can try letting our point be t and try solving it backwards. In other words, we can assume that the problem statement is true and try deducing what we know. So for one, we know that t lies on the perpendicular bisector of BC, so that means that it must be the midpoint of one of the arcs. And more realistically, it's going to be the midpoint of the arc containing A and D, and not the other one. So we can just let t be the midpoint of this larger arc. Now we want to show that t lies on the perpendicular bisector of EF. So we want to show that there's a circle centered at T passing through E and F. That's one way to interpret perpendicular bisectors. In general, whenever we have an arbitrary perpendicular bisector and we cannot immediately show that the lengths are equal or the angles are equal, then it's a good idea to draw a circle centered at T with radius EF. So as we see here, we have drawn the circle with center T and radius TE. And we want to show that it also has radius TF. In other words, that F lies on the circle as well. And if we're working backwards, then we just know that this circle exists. But wait a second. Look what other points it also passes through. It seems to also pass through these intersections with the circle. Let's go ahead and call them X and Y. So our first conjecture is that E, F, X, and Y are concyclic and with center T. And then we need to somehow use this to finish the problem, because then we know that the perpendicular bisector of EF and XY meet at point T, which is on the circumcircle. But then we need to show that the perpendicular bisector of XY is the same as the perpendicular bisector of BC. So our second conjecture is that BC and XY have the same perpendicular bisector. So now we just need to prove these two claims, and we will be done with the problem. So our first order of business is to prove that BC and XY have the same perpendicular bisector, since that's the easiest thing to do right now. And I've gotten rid of the circle at center T with radius TE, so we don't use circular reasoning, because that's the last thing we want to use in a geometry proof. So let's get started. We want to prove that BC and XY have the same perpendicular bisector, or that BCXY is an isosceles trapezoid. And the way to prove this is by either proving that BY equals CX, and it doesn't really seem that BY and CX are connected to each other as much, because BY isn't equal to any lengths we know. Or we can prove that bx equals cy. So let's do that instead. So we want to prove that cy equals bx. And in order to do this, one way is that we can relate them to a common length. In this case, since xz is parallel to AB, we know that bx is equal to AD. And since cy and AD are equal because AY and CD are parallel, that means that this is also equal to AD, and therefore these two are equal to the same quantity, which means that they are equal, and therefore BCXY is an isosceles trapezoid. All right, so now we just need to show that there is a circle with center T passing through E, F, Y, and X. And since we're assuming that T is a midpoint of the arc BC containing A and D, and we're working backwards, we know that Tx equals Ty. So if we can show that two more pairs of these lengths are equal, such as like Ty equals Tf and Tf equals Te, or Te equals Tx and Xt equals Tf, then we'd be set. So let's see what we can do. Well, we definitely don't want to use Te equals Tf because then we're just going backwards. So let's see if we can use Ty equals Tf or Tx equals Te in some way. Or we can use Ty equals Te or Tx equals Tf. If we use the former approach, then we want to show that Ty equals Tf. And this means that we have to introduce the perpendicular bisector of YF. And when we draw this, it doesn't appear like it goes through any nice points. So it doesn't seem like YF will be the approach. So let's instead try YE and XF, so that we want to show Ty equals Te and Tx equals Tf. Let's start with Ty equals Te and see if this is even a reasonable approach. So if we draw on this perpendicular bisector here, we get that it obviously passes through T, and then it also appears to pass through D. So this is definitely going somewhere. So let's see what's going on. We want to prove that Yt equals Te, and we know that for some reason D lies on the perpendicular bisector of Ye. To prove this, we can use DE. We want to prove that it's equal to dy, and this is where we use the problem condition for the first time. We have that DE equals AC by the problem condition, and now we just need to show that AC equals dy, but that's true because of the isosceles trapezoid ACDY. So that means that D also lies on the perpendicular bisector of YE. So let's go ahead and draw in YD, and DE is already drawn in. And we have YT, TE, and let's draw in DT. So if we could prove these two triangles are congruent, then this would obviously mean that T also lies on the perpendicular bisector, because then these two lengths are equal. So we have equal length 1, equal length 2, and now we just need an angle in order to prove that this last side is, these two last sides are the same. And then we have that we want to prove that these two angles are equal. But since T is the midpoint of the arc, and midpoint of the arc always lies on the angle bisector, this is just true. And therefore, by SAS congruence, we have that this is true. And that means that this is true as well by symmetry, because we can just apply the same argument with ATF and ATX. So therefore, combining all of these means that TE equals TY equals TX equals TF. And therefore, TE equals TF, and thus the perpendicular bisector of EF passes through point T. And since point T lies on the circumcircle of ABCD, and also the perpendicular bisector of BC, this implies that the perpendicular bisectors of BC and EF meet at a point T on the circumcircle of ABCD. And we are done. So, What's the main takeaway from this problem? Well, the only real difficulty in this problem came when we had to construct points x and y. And after this, we noticed that E, F, Y, and X were concyclic with circumcenter T, and using this, we could finish the problem. So the only unmotivated step is constructing X and Y, and at first glance, this seemed like a huge leap of faith to construct the circle centered at T with radius TE. However, when we're dealing with arbitrary perpendicular bisectors, like that of EF, it sometimes helps to draw this circle. Because if we look at triangle TEF, we don't see anything immediate about it. Like we don't know anything about angle TEF or angle TFE. So the best way we can relate TE and TF is by comparing them to other lengths. And when we want to compare them to other lengths, we just draw the circle centered at T with radius TE and see what lengths we come across. And by some miracle, we come across TX and TY. And that motivates the main claim for the problem, and we solve it. So thank you so much for watching this video, and I'll see you guys tomorrow for the next one.